The last transmission. There is a specific quality to the dark at this hour, not the absence of light exactly, more like the presence of something that light usually covers up. Something is already moving inside you right now, and it has been moving your whole life without asking. The signal goes out from one cell to the next, from one node in a long chain to the one waiting just ahead of it, and the chain does not stop, not for anything, not while you are reading this, or while you're thinking about reading this, or while your eyes are doing the small unconscious work of staying open. The signal just keeps going. You don't have to ask it to. This is where we are, not at the beginning of something, inside it, already deep inside a process that started before you knew you were in it, that will continue past the point where you are still paying attention, a process so continuous and so old that the only way to think about it clearly is to pretend for a moment that it could stop, to imagine the last pulse, to feel backward from silence to the sound that came just before silence, and ask what that sound was and where it went when it went. The word for this, the word scientists use once and then leave behind because the word is a door and not a room, is the Fermi Paradox, named for a physicist who asked a question at lunch and never fully answered it. The question was approximately, given how old the universe is, and given how many places in it could support the conditions for complexity, and given that complexity given enough time seems to lean toward more complexity, why has nothing out there ever said anything to us? The question sounds simple. It isn't. It has the quality of a thing that seems answerable until you actually try to answer it, at which point it opens into something much larger and much quieter than the original question suggested. But we are not there yet. We are inside a single cell at this particular moment. Before any of that, here is what the inside of a living process actually feels like if you could feel it, which you can't, not directly, but try. Constant, low level, chemically urgent, never fully at rest. The mitochondria in your cells are producing ATP right now in a process that runs on a gradient, a difference in concentration across a membrane so thin it is measured in nanometers. And that gradient drives a molecular machine that spins, actually rotates, about 100 times per second under normal conditions. And the product of that spinning is the currency your body runs on, and that currency is being spent almost as fast as it is being made, and none of this is happening because you decided to do it. None of this required a signal from you. It is simply what complexity does. It runs, it keeps going, it finds a way to sustain the conditions of its own running. And when those conditions shift, it compensates, and when compensation is no longer possible, well, that is the part we are building toward. Not yet. The chapter is expanding outward right now, but it will come back. It always comes back. The pulse goes out and the pulse returns, and that is true at the cellular level, and it is true at the level of the question we have been sitting next to without fully looking at. The question of the silence, the question of why the sky doesn't answer. We will be back there. For now, stay here, inside the machinery, inside the thing that is running without being told to run. The universe is about 13.8 billion years old. That number is large enough that it stops meaning anything after a certain point, not because it is incomprehensible exactly, but because comprehension requires comparison, and there is nothing useful to compare 13.8 billion years to. Your whole life, even a long one, is a rounding error so small it doesn't affect the final figure. The history of every civilization humans have ever built, stacked end to end, is still a rounding error. The time since the first fish pulled itself onto land and stayed there is a rounding error. These are not poetic observations. They are just what the arithmetic does when you run it. And the galaxy, just this one galaxy, the one we live in, contains something in the range of 100 to 400 billion stars. A meaningful fraction of those stars have planets. A meaningful fraction of those planets are rocky. A meaningful fraction of the rocky ones sit at distances from their stars where liquid water is at least theoretically possible, where the temperature range does not immediately foreclose the kind of chemistry that, on this planet, eventually produced everything from bacteria to the person lying awake right now thinking about bacteria. These are not contested numbers. The ranges are wide, and the uncertainties are real, but the general shape of the arithmetic is not in dispute. So, given all of that, given the age, the size, the sheer number of candidate locations, given that on at least one of those locations, complexity arose and sustained itself, and eventually started asking questions about the other locations, started sending signals out into the dark the way a cell sends a signal down a chain, without quite knowing where the chain ends. Given all of that, where is everyone? The question is not new. It is not even particularly unusual among the questions scientists ask, but it has a quality that most scientific questions don't have, which is that the silence that answers it is indistinguishable from the silence that would exist if the question were wrong. If no one is out there, the sky is quiet. If someone is out there and has chosen not to respond, the sky is quiet. If someone was out there and something happened to them, the sky is quiet. If someone is out there and has been responding for millions of years and we simply haven't built the right instruments yet, or haven't been listening on the right frequency, or haven't been listening long enough, the sky, from where we stand right now, is still quiet. The silence doesn't tell us which of these is true. It just sits there, doing what silence does. And here is the thing about sitting with a silence that could mean any of several completely different things. You start to notice what the silence feels like, and the feeling is different depending on which explanation you're entertaining at the time. If no one is out there, the silence feels vast and a little cold, the way an empty building feels at night. Not threatening, just uninhabited, just the absence of the thing that would fill it. If someone is out there and chose not to answer, the silence feels different, pointed almost, like a room where someone is awake but not speaking. That second kind of silence is the one we will be spending time with, not because it is the most likely explanation. It isn't obviously more likely than any of the others, but because it is the one that, when you look at it directly, looks back. The signal went out. 47 years ago, a dish in the Ohio countryside picked up a narrowband signal from somewhere in the direction of the constellation Sagittarius. A signal strong enough and structured enough and brief enough that the astronomer who noticed it circled it on a printout and wrote a single word in the margin. The signal was never detected again, not by that telescope, not by any other telescope in the decades of searching that followed. It lasted for 72 seconds. Then it ended. That is not a metaphor. That happened. The word the astronomer wrote was wow. We still don't know what it was. It probably wasn't what the margin note implied. The most cautious scientific interpretation, the one that accounts for the many ways that radio signals can behave strangely in the space between a star and a detector, suggests mundane explanations first. Interference, a satellite, something ordinary doing something ordinary in a way that looked, briefly, like something else. The mundane explanation is probably correct, but probably is doing a lot of work in that sentence, and 72 seconds is a strange duration for a coincidence. Back inside the cell, back inside the process that was already running when this chapter began and is still running now, still converting, still maintaining the gradient, still spinning the machine, still finding a way to sustain itself against the pressure of entropy that is always, slowly, working in the other direction. Back inside the thing that does not stop until it stops, and that, when it stops, stops all at once, and the signal that was travelling down the chain reaches the end of the chain and finds nothing waiting there to receive it. This is the contraction. After the expansion, after the galaxy, the stars, the billion candidate planets, the 72 seconds, this is where we come back to. Not to smallness as comfort, not to the body as refuge from the scale of the question, just to the fact that the question lives here too, inside the process, inside the thing that runs. The silence that surrounds the galaxy is not a different kind of silence from the silence that follows a signal's end. It is the same silence. We just haven't been able to hear it yet. Or we have. And that is what keeps the question open. Everything that can produce a signal eventually does start far enough away, and the Earth is a point, not a small circle, not a disk with weather patterns visible on its surface, a point, a single unresolved dot of reflected light in a vast field of other dots, indistinguishable from a planet that has never had a sea or a microbe or a thought about its own position in the dark. From that distance, nothing about it announces itself. Nothing says, this one is different. This one did something. Move closer, and things begin to accumulate. The dot becomes a sphere. The sphere has colour variation. The colour variation has a pattern. Blue patches that don't move in the same way as the white patches. Brown and green regions with their own slower cycles. None of this is conclusive. Other planets have colour variation. Other atmospheres produce stripes and bands and seasonal shifts that could, from a distance, be misread as signs of complexity. The universe is full of things that look interesting from far away and turn out to be geology. But keep moving closer. Let things settle into focus the way sediment settles in water, layer after layer, each one clarifying rather than complicating the layer below it. At some point, the atmosphere becomes legible, not to the eye, but to a spectrograph, an instrument that splits light into its component frequencies and reads the resulting pattern the way you might read a barcode, if barcodes told you the entire chemical history of a planet's surface and sky. The atmosphere of Earth, read this way, is a strange document. It contains oxygen in concentration that should not be there. Oxygen is reactive. Left alone, it combines with whatever it touches. Iron becomes rust. Organic compounds oxidize and break down. Surfaces change colour and composition. A planet with abundant free oxygen in its atmosphere is a planet where something is actively producing oxygen faster than the chemistry of the surface can consume it. The oxygen is a signal, Not a radio signal, not a deliberate signal, just a chemical fact that cannot be produced at that scale by geology alone. That layer settles. Below it, methane. Methane and oxygen coexisting in the same atmosphere is, from a chemistry standpoint, unstable. Methane oxidizes readily and should be consumed within decades if nothing is replenishing it. The fact that both gases are present simultaneously at detectable concentrations means something is producing both of them continuously. Not a volcano, not a hydrothermal vent, something biological. The methane is another layer settling quietly on top of the oxygen layer, and the combination of the two is, to a spectrograph reading from far away, something close to a signature. None of this required anyone to choose to signal. The atmosphere is not trying to announce itself. It is simply the exhaust of a biosphere going about its work. The chemistry of life running the same way the chemistry of an ATP synthase runs, not toward any destination, just forward, just continuing, just sustaining the conditions of its own continuation. The signal is incidental. It is the residue of process, not the product of intention. This distinction is going to matter later. For now, let it settle. There is a concept in physics called entropy, and it is one of those concepts that everyone has heard of, and almost no one fully believes, because what it actually says, if you follow it to its conclusion, is mildly disturbing in a way that is easy to ignore during daylight hours. The short version: systems tend toward disorder. Energy spreads out. Organized states break down into less organized states. The cup falls and breaks and does not reassemble. The hot thing and the cold thing left in contact eventually reach the same temperature, and after that neither of them is interesting anymore. This is thermodynamically inevitable. It is not a tendency. It is a law in the way that the word law in physics means something stronger than rule. It means a constraint on what the universe is permitted to do, and the universe has never, in any observation or experiment, been caught violating it. And yet, here we are, organized, persisting, converting energy from one form to another, exporting disorder into the environment at a rate just high enough to sustain local order, like a drain that keeps the water level down in a flooding room not by stopping the water from entering but by letting it out just fast enough. Life does not violate entropy. Life is an entropy engine. It takes in ordered energy, sunlight, chemical gradients, the potential stored in molecular bonds, and runs it through a process that produces more disorder in the surroundings than it produces locally, and skims the difference to maintain its own structure. The reason this matters here, now, in the context of the quiet sky, is this. The conditions that allowed entropy engines of this kind to arise on Earth were not obviously rare. They were not some vanishingly improbable configuration of variables that could only have occurred on one planet in one galaxy, at one moment in cosmic history. Water, carbon, moderate temperatures, a source of energy, enough time. These ingredients are not exotic. The universe makes them. It makes them everywhere. Whether it always uses them the same way is a different question. The first self-replicating molecules appeared on Earth approximately 3.8 billion years ago, possibly earlier. The fossil record and the chemical record are both imprecise at that scale, but the general window is not contested. What those first molecules looked like is still a matter of active research, but the broad mechanism is understood. Certain molecules, under certain conditions, can act as templates for their own reproduction. They don't intend to reproduce. They don't have intentions. They simply have a geometry that causes the right raw materials in the right concentrations to assemble themselves into copies of the template, and those copies become new templates, and the process runs forward. Once this is happening, something like selection begins. Copies that are better at persisting in the local environment make more copies. Copies that are worse at it make fewer. The population shifts. Over enough time and enough cycles, the population shifts enough that the descendants are functionally different from the ancestors, not designed to be different, just filtered. The filter is environment. The raw material is variation. The output eventually is everything that has ever been alive. None of this required a plan. None of it required an external agent to set it going. It required conditions. And the conditions, water, carbon, chemical gradients, energy input, time, are the same conditions that a spectrograph would describe as ordinary features of a moderately sized rocky planet at an appropriate distance from a reasonably stable star. Let that layer settle. The question is not whether life could arise elsewhere. The question, the one that sits underneath all the others, that the silence of the sky presses against without answering, is whether what comes after life, what life becomes when it has been running long enough and accumulating complexity long enough, whether that thing is as likely as the first step, whether the distance from self-replicating molecule to something that builds a radio telescope is a short walk or an enormous one, whether every pond that gets the chemistry right eventually produces something that looks up. Consider what it actually took on this planet for the chain to proceed, from the first self-replicating molecules to the first cells in the full sense, with a membrane and internal organization, and something like a division of labor, took roughly 1 billion years. From those first cells to cells with a nucleus, a separate internal compartment for storing genetic material, a structure so much more complex than what came before that its origin is still not fully understood, took another 1 billion to 2 billion years. From nucleated cells to multicellular organisms, where individual cells began to specialize and cooperate, instead of living entirely independently, took several 100 million more. This is a very long time to spend on transitions that, looking back from the other side, seem almost inevitable. 1 billion years is not a waiting period. 1 billion years is an active, continuous, churning period of variation and selection, and dead ends and near misses and environments that shifted, and mass extinctions that reset the populations and started the filtering over again from a different baseline. The tree of life is not a tree that grew steadily upward toward complexity. It is a tree that mostly grew sideways, that mostly stayed bacterial, that only produced large complex multicellular organisms in a narrow fraction of its branches, and only very recently. The Cambrian explosion, the relatively rapid diversification of complex multicellular animal life, happened about 540 million years ago. Rapid here means tens of millions of years. Humans, in their anatomically modern form, have been present for roughly 300,000 years. The agriculture that made cities possible is about 12,000 years old. The radio telescope is about 90 years old. The gap between the first molecule that copied itself and the first antenna pointed at the sky is 3.8 billion years wide. It is not clear that every planet with the right chemistry will take that path. It is not clear that most of them will. It may be that the path from chemistry to complexity is well worn, and the path from complexity to civilization is very narrow, and the path from civilization to a signal that reaches another star is narrower still. Or it may be that the path is wide and well travelled, and the sky is quiet for a completely different reason. Both of these possibilities are sitting here, in the space this chapter is making around them. Here is a thing that is easy to miss about the way complexity organizes itself. It doesn't have a direction, it has a tendency. The tendency is toward more efficient energy use. Given a space of possible configurations, the ones that process energy more efficiently tend to persist longer and replicate more successfully. Not because the universe rewards efficiency as a value, but because the configurations that are bad at energy processing tend to come apart. What remains is, on average, better than what was there before. Not better in any moral sense, just more stable, just more durable, just more capable of sustaining itself against the pressure that is always working to dissolve it. What this produces over billions of years is a kind of arms race between complexity and entropy. Not a race with a winner, just an ongoing negotiation in which complexity keeps finding new ways to hold itself together, and entropy keeps finding ways to erode whatever is holding it, and the forms that are alive at any given moment are the ones that have, so far, found a configuration the erosion has not yet reached. This is a story with no end point. There is no final stable configuration that life is building toward. There is no complexity level at which the negotiation concludes. Every increase in organization is also an increase in the number of ways that organization can fail. A bacterium has very few failure modes. A human being has an almost extravagant number of them. A civilization, an interconnected system of billions of human beings sharing resources and information across a planetary surface, has failure modes that don't even have names yet. The universe has been running this experiment on us for 3.8 billion years. The question underneath everything, the one this chapter has been layering toward from a long way off, is whether it has been running it elsewhere too, and if so, what the outcomes look like from the outside. Whether the outputs of all that selection, all that filtering, all those billions of years of complexity negotiating with entropy, whether those outputs are the kind of thing that produces a signal, whether they have to, whether they always do, whether the leaning, the slow, directionless, inevitable leaning of complex systems toward more complexity, ends up pointing at the sky. Return to the spectrograph. Return to the planet seen from far away, reduced to a dot of light, its atmosphere a thin chemical record of everything that has been living and dying on its surface for billions of years. The signal in the atmosphere was not sent, it was produced. The distinction feels important but may not be as clean as it sounds, because producing a signal over a long enough timescale, with enough consistency, in enough directions, starts to look a lot like sending one. The Earth has been broadcasting chemically for nearly 4 billion years. In the last 100 years, it began broadcasting electromagnetically as well. Radio waves, television signals, radar pulses, the entire electromagnetic exhaust of an industrial civilization, leaking into space at the speed of light in an expanding sphere that is now about 200 light-years across. 200 light-years is not very far. The Milky Way is about 100,000 light-years across. The bubble of our unintentional electromagnetic signature occupies a tiny, tiny fraction of the galaxy's volume, but it is expanding at the speed of light all the time, and it started. That is the layer that settles last, the one with the most weight, the one that changes how the ones below it feel. The signal from here went out. It went out because the chemistry went out first, and the complexity followed, and eventually the complexity built something that leaked into space without quite meaning to. The signal is out there. It is moving. It has been moving for a century, and it will keep moving for as long as physics permits, which is a very long time. Whether anything out there is in a position to receive it, whether there is any instrument pointed in our direction, sensitive enough, close enough, oriented correctly, is not something we can know yet. But the signal went, and somewhere in the logic of everything this chapter has been quietly building, the chemistry, the entropy engines, the billion-year march from molecule to mind, is the question that doesn't quite resolve before the chapter ends. If the conditions for all of this were not rare, if the leaning toward complexity is a general feature of the universe rather than a local accident, then why is the sphere of our signal still expanding into silence? Why has nothing come the other way? We chose the frequencies that felt like us. The ear is a good listener. It knows this about itself. That is part of the problem. We have been searching the sky for signals for about 60 years. The equipment has changed. The computing power has expanded by orders of magnitude. The number of frequencies we can monitor simultaneously has grown from a handful to millions. The methodology has improved in almost every measurable way, and we are, by any technical standard, much better at this than we were when we started. But the ear is still the ear. It listens in the ranges it was built to listen in. It interprets patterns according to the logic it was built with, and it was built by the same species that is doing the looking, which means the equipment, for all its genuine sophistication, is a self-portrait as much as it is a window. Here is the specific version of this problem, the one that stays close to the body. When humans decided which radio frequencies were most likely to carry a signal from an intelligent civilization, they reasoned as follows. A signal intended for another civilization would be sent on a frequency that that civilization was likely to be monitoring. A civilization advanced enough to send signals would be advanced enough to understand chemistry. A civilization that understood chemistry would know about hydrogen, the most abundant element in the universe, with a natural emission frequency of 1,420 MHz, a frequency so universal and so fundamental that it became a kind of shorthand for any civilization, anywhere, paying attention. The logic is genuinely careful. It is not naive. It rests on the assumption that physics is the same everywhere, that hydrogen behaves the same way in the Andromeda Galaxy as it does in a laboratory in New Jersey, and that assumption is almost certainly correct. Physics does not vary by address, but the assumption underneath the assumption is this, that any civilization advanced enough to send signals will have gone through a phase of development similar enough to ours that radio technology feels like the natural medium, that they will have discovered electromagnetism, that they will have built transmitters before they built whatever they built after transmitters, that the arc of their technological development passes through a point that looks, from the outside, like ours does right now, this is where the orbit begins. Because this assumption cannot be checked, we cannot look at a civilization that developed differently and assess whether it would have produced radio. We can only look at ourselves. We are the only data point, and we are using that data point to predict the behavior of an arbitrarily large population of others. There is a specific feeling, and this chapter is not certain it has the right name for it, so it will describe it instead. There is a specific feeling that arrives when you realize a tool you trusted was also, all along, a mirror. When the thing you were using to see turns out to have been showing you a reflection rather than a window. Not a dramatic revelation, more like a slow registration, a slight shift in how the room feels when the light comes through it at a different angle. The search for extraterrestrial signals has this quality when you look at it from a certain direction. We built instruments tuned to what we would do. We wrote protocols based on what we would send. We defined the parameters of a detectable signal based on what detectable signals look like to us. Narrowband, structured, non-thermal, anomalous against the background noise of natural processes. We assume that intelligence, wherever it arises, produces the same kind of anomaly that we produce, that it stands out from the background in the same way, that it looks, to a telescope, like us, and then we pointed the telescope at the sky and listened for ourselves. The sky didn't answer. But here is the thing the orbit keeps returning to. The silence might not mean no one is there. It might mean no one is there who looks like us. Which is not the same thing. Which is, in fact, a very different thing. A civilization 1 billion years older than ours, which is a number the age of the universe easily accommodates, which is a span of time we cannot feel but can write down, might not use radio at all. Not because radio doesn't work, but because they went through radio the way we went through fire, and stayed there for a while and then moved on. Whatever they use instead might not look like a signal to us. It might look like a natural process. It might look like background noise. It might be structured in a way that our pattern recognition, built by evolution to notice the things that mattered on a savanna millions of years ago, simply does not register. Or they might use something we haven't discovered yet, not hypothetically, factually. There are forces and phenomena in physics we know exist and do not yet fully understand. There may be forces and phenomena we don't know exist at all. If a civilization had access to a communication medium built on physics we haven't reached yet, their signals would be invisible to us the way a radio broadcast is invisible to someone who only has eyes. We would walk right through it. We are probably walking right through something right now. The ear is a good listener. That is still true. Within the ranges it was built for, it is extraordinarily sensitive. The searches conducted over the past 60 years have been genuinely rigorous, and the null result, the silence, is a real result, not nothing. But the ear was built by a particular kind of mind, shaped by a particular kind of history, tuned to a particular narrow band of what the universe is doing. The silence might be the answer, or the silence might be the shape of the question. This chapter has been orbiting that distinction for a while now. It is not going to resolve it. That is not a failure. Some distinctions need to stay unresolved a little longer. They lose something when you close them too fast, the way a room loses something when you turn the lights on before your eyes have had a chance to adjust. The ear is still listening. It hasn't stopped. Somewhere right now, a dish is pointed at a patch of sky it has already scanned 100 times, listening again in the frequencies that feel most like us, for something that sounds like it came from somewhere else. Whether that somewhere else is also listening on the same frequencies is a question the dish cannot answer from the inside. A planet that learned to be loud. 1895. Not yet. Almost. Marconi is 21 years old and working in the attic of his father's estate in Bologna, Italy, with equipment he built himself from parts of other equipment, testing whether an electric spark produced at one end of a room can cause a bell to ring at the other end of the room without any wire connecting them. The spark produces a pulse. The pulse moves through the air. The bell rings. This is not magic, and it is not an accident. It is a consequence of physics that Maxwell had already described mathematically 30 years earlier, which means the universe has known how to do this for a very long time. It just needed someone to build the right shape of metal at the right moment for the consequence to become audible. The bell rings. Marconi calls his mother up from the Sarden to witness it. She comes, and she sees, and the world has not yet changed, but the moment just before it changes has arrived and is sitting very still, the way things sit still at thresholds. This chapter follows that moment forward. It follows the thread, one thin, specific thread, from the bell in the attic to the edge of the solar system, and asks what the arc looks like from the outside, from far away, from a perspective that does not have our sense of the scale of a human lifetime, or a century, or an industrial age, from somewhere that would read the whole thing as a single event, a single breath, the way we read a mayfly's life as a single afternoon. By 1901, Marconi had transmitted a signal across the Atlantic, from Cornwall to Newfoundland, 3,500 kilometers, using an antenna erected in a field and a receiver consisting of a wire suspended from a kite. The signal was 3 dots, the Morse code letter S, and it lasted just long enough to be heard and noted and confirmed. 3 dots into the air from one side of the ocean, and a wire on the other side caught them, and a century of radio began. The thread from that moment moves through decades of layering, not acceleration, each decade adding a frequency range, a transmitter design, a use case the previous generation hadn't considered, amplitude modulation, frequency modulation, radar, which was developed quietly and in parallel in several countries during the 1930s, and which turned out to be extraordinarily loud, not to human ears, but to anyone listening the radio spectrum from a distance. Radar pulses are strong, directional, repetitive, and completely distinct from anything a non-technological planet would produce. If there is anything out there with a receiver, radar is the thing most likely to have introduced us, then television, then military communications spanning every continent, then satellite transmissions bounced off objects in orbit, filling the region above the atmosphere with structured electromagnetic traffic in frequencies that never existed in nature. Traffic that leaks outward at the speed of light in every direction, carrying in its patterns the unmistakable signature of something that learned to encode information and couldn't stop. The thread keeps going. Through the Cold War, which was, among other things, an enormous and sustained electromagnetic event visible from space, radar systems watching each other continuously, military communications running constantly, early warning networks pulsing at regular intervals like a planetary nervous system that had gotten frightened and couldn't fully relax. Through the late 20th century, when the total volume of electromagnetic radiation produced by human technology peaked and then began to change character, not to decrease, the total energy output of the civilization continued to grow, but to shift from loud, leaking broadcast signals to narrower, more directed, more efficient ones. Which is where the thread turns interesting. The transition from analog to digital broadcasting, which happened gradually between the 1980s and the 2010s across most of the world's major television and radio infrastructure, had a side effect that was not widely noted outside of a small community of people thinking about exactly this problem. It made the Earth quieter, not silent, not even close to silent, but measurably, detectably quieter in the specific frequency ranges that had been loudest during the broadcast television era. Analog television signals are relatively easy to distinguish from natural radio sources. They have a strong carrier wave, a predictable structure, a consistent spectral signature that nothing in nature produces. Digital signals, by contrast, look more like noise. They are intentionally compressed and spread across a bandwidth in a way that makes them carry more information per watt of power, but also makes them harder to distinguish from a distance from thermal background radiation. Fiber optic cables, which now carry a large fraction of the world's communications, don't leak into space at all. The signals stay in the glass. From the outside, they are invisible. Mobile networks transmit at lower power and shorter ranges than broadcast towers, and increasingly use beam-forming technologies that concentrate signals in specific directions rather than broadcasting omnidirectionally. The pattern across all these transitions is efficiency. The civilization is learning to use less power to do the same communication work, and to direct that power more precisely, rather than broadcasting it indiscriminately. This is rational behavior. It is economical. It is exactly what a technological civilization would be expected to do as it matures and optimizes its infrastructure. And from far away, it looks like the planet is going quiet. Here is the thread held up against the light. From roughly 1895 to roughly 1980, the Earth's electromagnetic signature in the radio spectrum increased year over year in power and in breadth, and in the distinctiveness of its structure. During this window, which is about 85 years long, which is less time than some of the trees currently alive on this planet have been standing, the Earth was at its loudest and most legible from the outside. The radar pulses were strong. The television carriers were structured. The military communications were omnidirectional and continuous. A sufficiently sensitive receiver at a sufficiently close distance, pointed in the right direction during this window, would have had a reasonable chance of detecting something anomalous. After this window, the signature becomes progressively harder to read. Not immediately, not all at once, but the trend is downward, toward efficiency, toward narrowcasting, toward invisible fiber, toward a planet that is still thoroughly technological, but increasingly hard to identify as such from the electromagnetic record alone. The window was about 85 years wide. Against the backdrop of cosmic time, against the 13.8 billion years the universe has been running, against the 4.5 billion years Earth has been here, against the 3.8 billion years life has been present on the surface. 85 years is a duration so brief it requires a kind of deliberate effort just to hold it as a real thing rather than a rounding error. Now think about what this implies for the search. For a civilization at a different star to detect our radio signature, several things would need to align. They would need to have their detector pointed roughly in our direction. They would need to be in the right distance range, not so close that we would already know about them, not so far that the signal has faded below detectability. They would need to be listening in the right frequency range, and they would need to be doing all of this during the specific 85-year window in which the signal was both strong enough and structured enough to be distinguishable from background noise. 85 years in a universe 13.8 billion years old. The arithmetic is not encouraging, but the thread turns again because this logic applies symmetrically. If we are hard to detect because our bright window was brief, then any other civilization that went through a similar arc, grew loud, then grew quiet and efficient, would have had its own brief window, and if we were not listening in the right direction, at the right frequencies during their window, we would not have caught them either. The galaxy could be full of civilizations that have already passed through their loud phase, each of them now transmitting only in narrow, directed, fiber-equivalent channels, each of them essentially invisible to any observer who wasn't there during the window. Each of them, from the outside, looking like silence. This is one version of the answer. It is called, in the literature that accumulates around this kind of question, the dark forest hypothesis by some, or more precisely described as a consequence of what happens when efficiency replaces broadcast as the dominant communication mode. Though the term covers a range of related ideas and the boundaries between them are not always clear. The version relevant here is not about hiding. It is simply about a civilization that has no reason to be electromagnetically loud anymore, and so isn't, and whose silence is not meaningful in any way except that it is indistinguishable from absence, which, if you're trying to detect it, is the same thing. The thread has one more place to go before the chapter ends. If the bright window of a technological civilization is brief, if the electromagnetic loudness is a phase rather than a permanent state, a transitional signature that appears and fades within a span of time that is tiny relative to the age of the universe, then what is the probability that any two civilizations, chosen at random from all the ones that might exist across the galaxy, would both be in their loud phase at the same time? The Drake equation, which was formulated in 1961 as a way of organizing the variables relevant to this question, includes a term called L, the length of time for which a civilization produces detectable signals. Drake himself, in the original discussion, used estimates ranging from 10 years to 10 billion years, because the honest answer was that no one knew. What the past century of our own technological development suggests is that the actual duration might be far closer to the low end of that range than the high end, at least for the electromagnetic signature that current SETI searches are designed to detect. If L is on the order of a few hundred years, which is not an unreasonable estimate given the transition from broadcast to narrowcast that we are already living through, then the probability that any two civilizations share the window narrows to something very small. They would need to be within a few hundred light years of each other to even have a conversation before one of them went quiet, and they would need, by extraordinary coincidence of timing, to be in their loud phases simultaneously. The galaxy has had time to run this experiment many, many times, with the parameters varied in every possible direction, in star systems scattered across a disk 100,000 light-years wide. What the current silence suggests, and this is not a conclusion, just a shape, just the outline of a possibility the evidence doesn't rule out, is that the windows might rarely, if ever, align, that the loud phases might be scattered so sparsely through time and space that the probability of two of them overlapping at the right distance and the right orientation is very close to zero. Or the windows aligned and we missed them, or we are early, or we are late, or we are typical, and the typical outcome of a technological civilization's electromagnetic history is exactly what we are watching happen to our own. A brief bright arc, a fade, a silence that doesn't mean the planet died, just that it stopped broadcasting. The bell rang. The mother came up from the garden. Somewhere a wire caught 3 dots, and the window opened, and the window is closing, and that is not the end of the story. It is the shape of a chapter in a story that is still going, even when the signal gets too faint to read. What water remembers? The reaction is already running when we arrive here. It has been running for a while, inside a hydrothermal vent on the ocean floor, not a metaphor for something else, an actual structure, a chimney of rock and mineral precipitation rising from the seafloor in the dark and the cold, somewhere between 2,000 and 4,000 meters below the surface. The chemistry that may, or may not, have preceded life on this planet is going right now, in the present tense, without any supervision, without any knowledge of the question it is helping to answer. Hydrogen sulfide moving up through the rock, meeting seawater moving down, temperature gradients steep enough to drive reactions, minerals precipitating on the vent walls, creating tiny compartments, porous, irregular, chemically active, that, under the right conditions, function as primitive reaction chambers, concentrating molecules that would otherwise drift apart before they could do anything interesting. The chemistry running in these systems is genuinely complex, and it has been studied seriously since the late 20th century, and the consensus among researchers who work on the origin of life is not that hydrothermal vents are certainly where life began, but that the conditions in alkaline hydrothermal vents in particular, lower temperature, pH gradient, mineral-rich walls, provide a plausible environment for several of the most stubborn early steps. The proton gradient across vent walls is chemically analogous to the proton gradient that drives ATP synthesis in every living cell today. Not identical, analogous. As if the cellular machinery that powers all life inherited a logic from the chemistry that existed before the cell, from the mineral walls of a structure that didn't know it was doing anything important. We are beside this, not inside it. We are watching it the way you watch something you have heard described but never seen, with a combination of recognition and unfamiliarity, the sense that the shape is right, but the scale keeps being wrong, keeps being either too large or too small for the imagination to hold without adjusting. Zoom out. How many places in the universe have liquid water? This is where the chapter's density begins to show, because the honest answer is, we don't know, but the lower bound is higher than most people expect, and the shape of the uncertainty is interesting. Water is not rare. Hydrogen is the most abundant element in the universe. Oxygen is the third most abundant. Their combination is chemically stable, abundant in molecular clouds, and has been detected in interstellar space, in comets, in asteroids, and on the surfaces and subsurfaces of numerous bodies in our own solar system. The question is not whether water exists elsewhere. It clearly does. The question is whether it exists in liquid form, which requires both the right temperature and the right pressure, conditions that are more constrained than the mere presence of the molecule. On the surface of a rocky planet, liquid water requires what astronomers call the habitable zone, the range of orbital distances from a star at which surface temperatures could, in principle, permit liquid water, assuming an atmosphere of appropriate composition. The range is not fixed. It depends on the star's luminosity, the planet's albedo, the greenhouse effect of the atmosphere, and several other variables. For Sun-like stars, the habitable zone sits at roughly 0.95 to 1.4 astronomical units from the star, though different models give somewhat different numbers. Earth sits at 1.0, Mars sits at 1.5, just outside most estimates, though it had liquid water on its surface at least episodically in its early history when its atmosphere was denser. But surface habitability is only one kind of habitability, and it may not even be the most common kind. Europa, Jupiter's moon, a body about the size of our moon, orbiting a planet so large that the tidal forces generated by Jupiter's gravity flex the moon's interior like a squeezed rubber ball, generating heat through mechanical friction in the rock and ice. The surface is frozen. Temperatures at the surface are around minus 160 degrees Celsius. From space, it looks like a cue ball with brown streaks across it, long fractures in the ice, where the surface has cracked and refrozen, tinted by salts and possibly organic compounds welling up from below. Below the ice, which is estimated to be somewhere between 10 and 30 kilometers thick, depending on location and method of estimation, there is very likely a global ocean of liquid salt water, not a hypothesis, a conclusion supported by magnetometer data from the Galileo spacecraft, by the morphology of the surface features, by thermal modelling, and by the detection of water vapour plumes erupting from the southern region that resemble, in their structure, the geysers on Enceladus. The ocean beneath Europa's ice may contain more liquid water than all of Earth's oceans combined. Europa is not in the habitable zone. It is 5.2 astronomical units from the Sun. It is frozen on the surface, and it has a global liquid ocean, possibly for billions of years, possibly in contact with a rocky seafloor, possibly with hydrothermal activity that produces the same chemistry that runs in the vents where we started this chapter. Enceladus, a moon of Saturn, much smaller, about 500 kilometers across, has active hydrothermal vents confirmed by the Cassini spacecraft, which flew through its plumes and detected hydrogen, carbon dioxide, and a range of organic molecules, including complex ones, in concentrations that are consistent with ongoing hydrothermal chemistry at the ocean floor. The vent chemistry on Enceladus is, as far as we can tell, operating in a range that partially overlaps with the chemistry that is thought to have preceded life on Earth. Titan, also orbiting Saturn, has lakes and rivers, but of liquid methane, not water, at a surface temperature of minus 179 degrees Celsius. The chemistry that might arise in a liquid methane solvent is different from aqueous chemistry, and is genuinely unknown in terms of its potential for producing self-replicating structures. It may be that water is not the only liquid capable of supporting the relevant chemistry, and that Titan represents a second, entirely distinct type of environment to consider. Or it may not. The methane lakes on Titan are real. What is in them is not yet known. Just in our own solar system, Earth's oceans, Europa's subsurface ocean, Enceladus's ocean, possibly Ganymede, possibly Callisto, possibly Ceres, Titan's methane seas. Mars had liquid water on its surface for perhaps 700 million years in its early history, long enough for complex chemistry to have run, whether or not it did. 8 planets, dozens of moons, several locations with liquid water or liquid something, active chemistry, energy gradients in one solar system. The Milky Way contains somewhere between 100 and 400 billion stars, and the observable universe contains an estimated 2 trillion galaxies. Back to the vent, back to the reaction running in the dark. The question that this chapter is sitting beside, that it has been approaching from the outside like you approach a fire that is hot enough to be worth approaching carefully. The question is whether the chemistry that ran in environments like this one, on this planet, roughly 4 billion years ago, is likely to have run the same way elsewhere. Not identically, not producing the same molecules in the same sequence on a predetermined schedule. Just whether the combination of liquid water, chemical gradients, energy input, mineral surfaces, and time is sufficient in general to produce self-replicating chemistry, regardless of the specific minerals or the specific molecules or the specific sequence of events. The honest answer is that we do not yet know. This is not a gap that will be filled by a single experiment. It is a gap that will be filled, if at all, by a combination of better understanding of the chemistry of the origin of life on Earth, which remains genuinely incomplete, and direct investigation of other environments, like Europa and Enceladus, which is underway but slow, because getting instruments to those places takes decades and billions of dollars and successful landings, and the right question asked of the right instrument in the right way. What we do know is this: the conditions are not rare, the ingredients are not rare, the energy sources are not rare. What may or may not be rare is the specific sequence of events that transforms a set of favourable conditions into a self-replicating system, a sequence that, on Earth, took hundreds of millions of years to complete and left almost no direct evidence, only the chemistry of the systems it produced, read backward like a receipt with most of the text worn off. The receipt is legible enough to tell us something happened. It is not legible enough to tell us exactly what or how likely it was, or whether it would happen again under similar conditions or only once in a very long time, and we were simply there to see it because we are, by definition, the result of it having happened. That last possibility, the one where we are here because life arose, rather than life arising because the conditions made it likely, is the anthropic reasoning that makes this whole question genuinely difficult to assess. We cannot observe ourselves in a universe where life didn't arise on Earth. We can only observe the one we are in, which is by definition one where it did. Whether the conditions that produced us are common or rare, the view from inside is identical in either case. We would look out at the universe and see the same sky either way. Zoom out further, past the solar system, past the nearest stars, past the Orion arm of the Milky Way into the wider structure of the galaxy. and consider for a moment what the distribution of habitable environments might actually look like at galactic scale. The galactic habitable zone is a concept proposed in the early 2000s by Charles Lineweaver and colleagues, a region of the Milky Way, roughly an annular band centered on the galactic plane at intermediate distances from the galactic center, where the conditions for complex life might be most favorable, not too close to the center, where stellar density is high and radiation events and gravitational disruptions are more frequent, not too far from the center, where metallicity is low and the heavier elements needed for rocky planet formation are less abundant. The Sun sits near the inner edge of this proposed zone, which is thought to span roughly from 7 to 9 kiloparsecs from the galactic center, though the concept remains debated and the boundaries are not sharp. Within this zone, stars formed at different times. The galaxy is about 13.6 billion years old, and star formation has been ongoing throughout, producing generations of stars with progressively higher metallicity, as each generation seeds the next with the heavier elements produced in its cores and scattered in its depths. Stars that formed several billion years before the Sun would have had time, in principle, for life to have arisen and evolved and either persisted or ended before anything resembling a human being existed on Earth. A civilization that arose on a planet orbiting a star formed 8 billion years ago, if that is possible, if the metallicity of early stars was sufficient for rocky planet formation, which is uncertain but not ruled out, would have a billion-year head start on us. Not a century, not a millennium, a billion years, and we would currently be looking out at the silence that followed everything it did or didn't do in that billion years, with no direct way to know which. Back to the vent, all the way back. The reaction is still running. The hydrogen sulfide is still moving upward through the mineral walls. The temperature gradient is still there. The compartments in the rock are still concentrating molecules that have nowhere better to be. Nothing in this system knows it is doing anything. Nothing is being attempted. The chemistry just goes, the way everything goes when the conditions permit it to go, the way the ATP synthase just goes, the way the signal in a cell just goes, the way a civilization's electromagnetic signature goes when the civilization learns to transmit. What the vent represents is not the origin of life. It is the conditions for the origin of life, which is a different thing and a more unsettling one. Because the conditions are here. They are present. They are running right now in multiple locations in our solar system, and in, by reasonable extrapolation, an enormous number of locations across the galaxy. The conditions are not the bottleneck. The conditions seem to be everywhere. What the bottleneck is, where, in the chain from chemistry to self-replication to complexity to civilization, the narrow point actually sits, is the question this chapter has been circling from the moment it opened. And the honest answer, the one that the science as it currently stands actually supports, is that we don't know where the bottleneck is. We know there is one, because the sky is quiet. We know it exists somewhere in the chain. We cannot yet see clearly enough into the chain to say which link it is. Maybe the first link, maybe the last, maybe one we haven't identified yet. The vent doesn't know. It just runs. Something that existed for 11,000 years and then stopped. The city of Çatalhöyük, in what is now south-central Turkey, was inhabited for roughly 1,400 years, from about 7,500 BCE to about 5,700 BCE, and at its peak it housed somewhere between 5,000 and 10,000 people, which made it one of the largest human settlements in the world at that time, and then it was abandoned. Not destroyed by conquest or fire, as far as the archaeological record shows, just left. The people went somewhere else, or dispersed into smaller settlements, or shifted their patterns of habitation in ways that the soil and the artifacts only partially record. The buildings were not burned. The grain stores were not emptied in a rush. The place was left, and then the grass came, and then the soil came, and then the silence came, and it stayed quiet for about 8,000 years before a British archaeologist named James Mellart began excavating it in 1958. This is not a story about a lost civilization. Çatalhöyük was not exceptional. Hundreds of settlements like it rose and declined and dissolved back into the land across the span of the Neolithic and Bronze Ages, each one representing a kind of experiment in collective organization, a group of human beings trying a particular arrangement of shared space and shared resource management, sustaining it for a while, and then stopping, for reasons that are sometimes clear and sometimes not. What they all share is a duration, and the duration, when you hold it up against the question this book has been carrying since the first chapter, has a specific weight to it. 11,000 years is the approximate age of the oldest evidence of organized, settled human civilization. The transition from nomadic hunter-gatherer societies to communities with permanent or semi-permanent structures, agriculture, and the kind of social organization that produces both grain storage and ritual burial. That transition began in different places and at different times, somewhere around 10,000 to 12,000 years ago. The oldest known temple complex, Göbekli Tepe in southeastern Turkey, dates to approximately 11,500 years ago, a structure built by people who were, based on the faunal record, still primarily hunter-gatherers, which complicates the standard narrative about the sequence of agriculture and monument building, but does not change the basic timeline. Organized human complexity, in any form that has left a legible architectural record, is about 11,000 to 12,000 years old. Homo sapiens, in anatomically modern form, has been present on Earth for roughly 300,000 years. For about 290,000 of those years, the species left almost no permanent structures, no agriculture, no cities, no writing. Then, in a span that is less than 4% of our total existence as a species, it built everything that we currently think of when we say civilization. Whether that rate of change is fast or slow depends entirely on what you are comparing it to, and that comparison is exactly what this chapter is drifting through. There is a term in the literature on civilizational risk, not a scientific term, more of a conceptual scaffold, called the Great Filter. It was proposed by economist Robin Hanson in 1998, and it refers to whatever process or processes in the development of intelligent life are so difficult to survive that almost no civilization makes it past them. The idea is that the silence of the sky implies the existence of such a filter, something that eliminates or prevents or ends the vast majority of potential civilizations before they can produce a detectable, durable signal. The filter could be behind us. The transition from prokaryotic to eukaryotic life, from simple cells without a nucleus to the more complex nucleated cells that are the basis of all multicellular life, may have been the filter. It took roughly 2 billion years to occur on Earth, and may represent a genuinely improbable step, one that succeeded here and failed everywhere else. If so, the galaxy is probably full of bacterial mats and empty of everything else, and the silence is simply the silence of a universe that got most of the way to complex life and then stalled. Or the filter could be ahead of us, somewhere between where we are now and the production of a truly durable galaxy-spanning signal, not 200 light-years of leaking broadcast television, but a signal intended to persist and reach and be received. There may be a transition that almost nothing survives, a technological threshold, an ecological threshold, a social threshold, something that every civilization in the history of the galaxy has approached and almost none have crossed. The honest assessment of the evidence does not tell us which of these is correct. It does not even strongly favour one over the other. Both are consistent with what we observe. What they both imply, sitting quietly in the residue of this chapter's opening thought, is that 11,000 years of organised human civilization may or may not be a long time in the relevant sense. It is long relative to a human life. It is essentially nothing relative to the age of the universe. Whether it is long relative to the typical lifespan of a technological civilization is the question, and it is the question we cannot answer from inside the only data point we have. Here is what the archaeological record does say, quietly, if you spend enough time with it. Civilizations end. They end regularly. They end in ways that are sometimes catastrophic and externally caused, and sometimes slow and internally driven, and sometimes somewhere between. A weakening of the conditions that made the original organization possible. A shift in climate. A change in the resource base. A political fragmentation that no single generation intended, but that accumulated across enough generations to become structural. The Roman Empire's western half went down over a period of roughly 2 centuries, and it had been showing the particular kind of structural stress that precedes that kind of decline for at least a century before the end, and the people living through it mostly did not experience it as a civilization ending. They experienced it as things getting harder, administrations becoming less reliable, roads being maintained less well, trade routes becoming less safe. The end was not a sound. It was a fading. The Bronze Age collapse around 1200 BCE was faster, a period of roughly 50 years during which several interconnected palace economies across the eastern Mediterranean and Near East went silent. The long-distance trade networks that had sustained them broke down. Writing systems were lost. Population centres were abandoned. And several centuries of what might loosely be called a dark age followed. The cause is still debated. Climate change, migration, internal social pressure, systems collapse from a combination of stressors. The evidence supports several hypotheses and none of them cleanly. What is consistent across these events is not the cause. It is the aftermath, the silence after, the grass coming back, the soil coming back, and eventually, sometimes, people coming back, different people or the same people organized differently, building on the foundations or not finding the foundations at all, and beginning again from a baseline that does not include the knowledge of what was there before, because that knowledge did not survive in any form they had access to. The arithmetic of duration, held against the backdrop of what the sky's not saying, goes like this. If civilizations are common in the galaxy and their average lifespan, the window between the first organized complexity and the last is on the order of thousands of years, then most of them are already over. Their signals, if they produced any, are already past us. The sphere of their electromagnetic history is already expanding beyond the point where any receiver we could build would catch it. They existed. They had their window. They faded. The grass came back, and no one who came after knew what had been there, and the sky received no message about it. If their average lifespan is on the order of millions of years, then some of them may still be running, and the silence is a question of distance and frequency and timing. The problem this book has been turning over since the first chapter, rather than a question of survival. If their average lifespan is on the order of billions of years, then the silence becomes very hard to explain by any means other than scarcity. A civilization that has been running for 1 billion years and is still running should, by now, have had time to make itself known in almost any way you can imagine. Not necessarily by radio, but by something. By the evidence of what 1 billion years of technology does to a star system, by the waste heat of computation at scale, by the restructuring of orbits, by something. The absence of that something, in all directions, at all frequencies we can monitor for as long as we have been looking, is its own kind of answer. 11,000 years. That is what we have so far. Whether that is most of our total duration or a very small fraction of it is a question we are living inside without being able to see the answer. The way Çatalhöyük's inhabitants were living in a city that would be empty grass in a few generations, building their grain stores and their shrines and their dense mud brick rooms in a pattern they had no particular reason to believe would not continue. The city ran, it kept going, and then, for reasons the soil only partially records, it stopped. The part of the sky that has not arrived yet. On a clear night you can see the Andromeda galaxy with your naked eye, if you know where to look and the sky is dark enough and your eyes have had time to adjust. It appears as a faint smudge slightly above and to the right of the constellation Andromeda itself. Not a point like a star, but a diffuse oval of light, soft at the edges, brighter at its centre. It is the most distant object visible to the unaided human eye. Most people who see it for the first time underreact. They expect something grander. They get a smudge. But the smudge is 2.537 million light-years away, and what you are seeing when you look at it is the accumulated light of roughly 1 trillion stars travelling for 2.537 million years to reach your retina. 2.537 million years. Human beings, Homo sapiens, anatomically modern, have only existed for about 300,000 years. The light you're seeing from Andromeda left its source when our ancestors were Homo ergaster, a species that used hand axes and fire and had brains substantially smaller than ours, and those photons have been in transit ever since, through the expanding space between galaxies, untouched by anything, until they arrived in your eye on a dark night in the present. This is not a metaphor, and it is not a rhetorical device. It is geometry. It is how light and time interact in a universe where light has a finite speed and space is very large. It is the first thing to understand, and possibly the most disorienting, because once you have it, the sky stops looking like a picture of what exists and starts looking like a record of what existed, with different parts of the record corresponding to different depths of the past. The nearest star to the Sun is Proxima Centauri, approximately 4.24 light-years away. The light you see from Proxima Centauri left it 4.24 years ago. If something happened to that star today, if it went dark, if it flared dramatically, if a planet orbiting it suddenly began producing a large and structured electromagnetic signature, you would not know for 4.24 years. Not because the information is being delayed or withheld, but because 4.24 years is how long it takes for anything to travel from there to here. At 100 light years, whatever is happening there now will not be known here for a century. At 1,000 light years, a millennium. At 26,000 light years, the approximate distance to the galactic center, a signal sent from Earth today will not arrive there for 26,000 years, and a signal sent back in response will take another 26,000 years to return. A conversation between Earth and the galactic center at the speed of light takes 52,000 years per exchange. One question, one answer, 52,000 years. These are not astonishing numbers in the sense of being unexpected. The physics has been understood for well over a century. They are astonishing in the sense that they do not stop being astonishing, no matter how many times you look at them, the way a large enough number stops being a number and becomes more like a texture. Here is the geometric problem at the center of the silence. Suppose there is a civilization orbiting a star 1,000 light-years from Earth. Suppose that civilization produced a strong, structured radio signal for about 500 years, a window, as discussed in earlier chapters, that is generous relative to our own current trajectory, and then shifted to more efficient, less detectable communication modes. The signal was broadcast omnidirectionally. It expanded outward as a sphere at the speed of light. 500 years worth of signal, a spherical shell 500 light-years thick, moving outward at sea. That shell left its source. It has been moving for, say, 2,000 years. The leading edge is now 2,000 light-years from the source. The trailing edge is 1,500 light-years from the source. Earth is 1,000 light-years from the source. Depending on the exact timing, depending on when the civilization started broadcasting and when it stopped, Earth may currently be inside the shell, receiving the signal right now without knowing it. Or it may be behind the shell, in a region of space the signal has already passed through and moved on from. Or it may be ahead of the shell, in a region the signal hasn't reached yet. We cannot know which of these is true without knowing the exact timing, and we have no way to know the exact timing. The sky we can observe at any given moment contains signals that are already past us, signals that are currently arriving, and signals that haven't reached us yet. We have access to only the middle category. The first category is gone. The third category is coming, and we will not know it is coming until it arrives. And if we are not listening in the right direction at the right frequency at the right moment, we will not know when it does. The observable universe is about 93 billion light-years in diameter. This is not a typo, and it is not a mistake. The universe is about 13.8 billion years old, but the regions that emitted the light we can currently observe have been moving away from us for the entire duration of cosmic expansion, which means they are now much further than 13.8 billion light-years away. The universe's expansion has been carrying them outward the whole time, and accounting for that expansion gives a current diameter of the observable universe of approximately 93 billion light-years. Within that volume, the number of stars is estimated at around 10 to the 24th power, a 1 followed by 24 zeros, 10 septillion, a number that the brain processes as a texture rather than a quantity. Most of those stars are beyond any range that allows for the kind of communication we have been discussing. Even at the speed of light, even given civilizations that are 1 billion years old, the sheer scale of the observable universe means that most of it is effectively isolated from most of the rest of it. Not by intent, not by choice, but by geometry and the finite speed of information. The sky we see is a thin, bright slice of what has happened. The darkness between the stars is not empty space. It is space full of things that happened too long ago or too far away, or on a timeline that hasn't reached us yet. The silence is not the absence of events. It is the limit of the record. Back to Andromeda. The smudge. The light that left 2.5 million years ago and arrived just now. It's still there. Still faint. Still a smudge. Somewhere in it, if the arithmetic of habitable zones and the chemistry of self-replication and the long odds of civilizational survival all landed right in at least one place among its trillion stars, there may be something looking back. Something that sees our galaxy as we see theirs, a faint oval, diffuse at the edges. Something that is, right now, or was 2.537 million years ago in a way that amounts to the same thing from our side, looking at the light that left the Milky Way when our ancestors were still learning what fire was for. Whatever answer that looking produces, if it produces one, will not arrive here for another 2.537 million years. The timeline of contact is not a line we can see both ends of. We are standing at one end. The other end, if it exists, is somewhere in a direction we can point at but not reach, at a time we can calculate but not live to see, carrying information about a moment that will be long past by the time the information arrives. The geometry makes this true regardless of what is out there. It is simply what happens when the universe is as large as it is and light is as slow as it is relative to the distances involved. There is no workaround. There is no exception. There is just the speed and the distance and the patience required to understand what looking at the sky actually means. You're not seeing now. You're reading a record. The record has gaps. Some of the gaps are geological, some are civilizational, and some are simply the spaces between the words in a message that hasn't finished arriving. The feeling returns. The arguments have been made, the chemistry has been described, the distances have been measured and the timelines have been written out, and the silence has been looked at from several different angles, each one yielding a slightly different shape, none of them resolving into a single clean answer. The chapter you're in now is the one where the narration stops adding new information and simply sits with what has accumulated, the way you sit in a room where a long conversation has just ended, and the air still holds some of the weight of what was said. There is nothing in this chapter that was not in the earlier ones, but the earlier chapters are behind you now, and having them behind you changes how the silence feels. It has more content. It carries more possible meanings. The same dark that was there at the beginning of this book is still there. It was always there. It will keep being there. But now it is populated, or possibly populated by hydrothermal vents and dead civilizations and signals that missed us by 1,000 years, and minds that chose to go inward instead of outward, and the ghost of a 72-second pulse in the direction of Sagittarius that no instrument has ever caught again. The silence contains all of that now. It didn't before. You put it there by going through the earlier chapters, and it does not come back out. The body is still running. It has been running through all 9 chapters without being asked, without pausing while the ideas moved through. Somewhere in the brain stem, a structure so old in evolutionary terms that its basic architecture is shared by creatures that diverged from the human lineage hundreds of millions of years ago. A cluster of neurons is managing the rhythm of breathing right now, adjusting the depth and rate in response to carbon dioxide levels in the blood, not because anyone decided to breathe, but because the system runs, and the running has never required a decision. The heart is going, the cells are converting, the signals are moving down their chains. This is what it means to be a process rather than a thing. You're not a stable object that thinks. You're a continuous event that, among other things, thinks. And that event, the running of you, the ongoing chemical negotiation with entropy that has been going on since before you were born and will stop, eventually without warning, is the same kind of event at a radically different scale as the event that produced the oxygen in Earth's atmosphere, and the event that first caused a molecule to copy itself in the water of an ancient sea, and possibly the event that, somewhere else, produced something that sent a signal, or decided not to, or went so quiet that the difference no longer matters from here. The continuity between those events is not a metaphor. It is chemistry. It is the same entropy engine at different scales, in different arrangements, doing what entropy engines do, running, converting, exporting disorder outward, sustaining the conditions of their own continuation for as long as the conditions can be sustained. What the silence actually means is still not known. This is a real statement, not a rhetorical hedge. The Fermi Paradox remains unresolved. The null result of 60 years of radio searches is a genuine null result, with genuine implications, but those implications are consistent with several mutually exclusive explanations, and the science currently in existence does not have the tools to distinguish between them. New telescopes will help. The James Webb Space Telescope has already begun producing atmospheric spectra from exoplanets, the first preliminary steps toward the kind of biosignature detection that could, in principle, tell us whether the chemistry of life is common or rare. Missions to Europa and Enceladus, if they proceed and succeed, could do the same for the question of whether life arose independently in our own solar system. A single positive result from either direction. A biosignature in an exoplanet atmosphere, a microbe in a European ocean, would not answer everything, but it would change the weight of the question substantially. It would tell us the first step is not the filter. It would tell us life, at least in simple form, can arise more than once. It would shift the question forward in the chain, past chemistry, past simple life, toward the long road from microbe to mind, and whatever lies on the other side of that road that we have not yet been able to see. We do not have that result yet. We have the silence. There is a particular quality to lying still and knowing that the galaxy is rotating overhead, not quickly at human scales, but measurably, in a way that can be confirmed by instruments. and that the rotation has been going on for billions of years, and that somewhere in the slow wheel of it, in the long arms of it, in the dense old stars toward the centre of it, and the young hot stars at the rim, the same conditions that produced the process running quietly in this body may have produced other processes, and those processes may or may not have reached the point of wondering, and if they did, they may or may not still be running, and the wondering, if it happened, may have produced a signal, and the signal, if it was sent, may or may not have passed through this region of space at a time when something here was in a position to catch it. Maybe it did. Maybe it is coming. Maybe it already went by. And the galaxy keeps turning, and the body keeps going. And the dark at this hour has the specific quality it has because of where the planet is in its rotation right now. With this hemisphere tilted away from the sun, the light gone, the temperature dropping slowly toward whatever the night's low will be, the brain stem managing the breathing without being asked, the mitochondria running, the signals passing down their chains, the carbon that was once a star and before that a cloud and before that something we don't have a name for. That carbon, in this particular arrangement, still here, still running, still in the middle of the event. The silence doesn't end. It is still there when you close your eyes. It was there before this started. It will be there after. That is not a conclusion. That is just the thing that remains when the chapter is over, and the room has gone quiet and whatever was said is still hanging in the air, not quite finished settling, probably not going to finish settling, doing what it does in the dark when no one is listening.